Okay, so I now just want to do an analysis of this solution. So this is just the solution, same problem from the previous video. This is the solution. I want to talk a little bit about it. So let's imagine you are sitting at this point, x equals 2, and you set up a little monitoring station and you monitor the amount of wood chips that flow past. And so you start here, and as time progresses, it kind of goes along this arrow here. Now, you're going to have 0 wood chips up until you get this point. So if you look at this particular problem here, for example, or sorry, this solution here, we want to look at a particular point, x is equal to 2. So we're going to have this, like this. We're going to have a 2 here, and we're going to have a 2 here. Now notice that you start here, like when t is equal to 0, you start here. As time increases, this is decreasing, and so you start above 2. Like you start so that this value is bigger than 2, and as t increases, eventually you're going to get to a point right there when e to the minus t times 2 plus 1 is exactly equal to 2. Okay, so in other words, e to the t times 2 plus 1, that's equal to 2. 2 minus 1 is 1, and e to the minus t. So what's going to happen, again, if you set up a monitoring station at a certain time, that is, when this, the t value for which this is equal to 2, is going to go from having a concentration of 0 wood chips per whatever to a concentration of e to the minus t wood chips. And over here, when this is equal to 2, e to the minus t is going to be equal to 2 over that, which is 2/3. So what's going to happen as you wait at your monitoring station and the water flows by, there's going to be no wood chips, no wood chips, no wood chips, no wood chips. All of a sudden, at a certain time, that is when that is equal to 2, there's going to be a concentration of 2/3 wood chips per whatever, okay, whatever the units are. So you're going to go from 0 wood chips to some wood chips. And you're not going to gradually ramp up to those wood chips. You're just going to see those wood chips. Now this makes sense because, so there's a discontinuity, right? There's a discontinuity. Physically this makes sense because the wood chips are flowing by and you just see that front of wood chips. Remember, there's an initial concentration that goes from 0 to 1 at x is equal to 1. And as the river moves those wood chips along, you're going to see that front, and there's going to be a discontinuity. It's going to be like a infinitely fast jump up from 0 concentration to some concentration. Physically, that makes sense. There's no problem with that. Mathematically, it makes sense as well. Functions are allowed to be discontinuous, and then what's going to happen is going to ramp down, and when this quantity is equal to 1, okay, so if this quantity is equal to 1, is 1 minus 1, that's 0. There's going to be 0 wood chips, and that'll be, at a certain time, whatever value of t makes that equal to 1. Now, there's not a discontinuity there, but there is going to be, it's not going to be differentiable there because our initial data is not differentiable at 0. Okay, so what's happening here? If you remember the theorem that we talked about, the existence uniqueness theorem, it said we're supposed to have continuously differentiable solutions. But remember, that's only if our initial data is continuously differentiable. Since our initial data is not continuously differentiable, then our solution is not going to be continuously differentiable. In general, the solutions are only going to be as regular, that is as continuous, differentiable, whatever, as the data in the problem. Again, this is unlike what we saw with second order equations like the diffusion equation and the Laplace's equation, but it's similar to the wave equation. We don't get extra irregularity here. First order equations are just kind of all about moving things along. They're not about smoothing things out. It's just about moving things from one spot to another. That's why, these are called transport equations. Okay, so if we just think mathematically, so forget that we have this idea about, the wood chips or whatever's happening. If we just say, let's find a solution that satisfies this equation, and if we stipulate that we're okay with discontinuous solutions, why not have this as the solution? U of xt is equal to 0 if t is bigger than 0 and x is equal to 0 and it's equal to g, on our curve gamma, where g of x is going to be the function that's, g of xt is the function that's 0 there, it's x from there to there, and 0 afterwards. In other words, just what the initial data needs to be. So this definitely satisfies the PDE, because if u is equal to 0, that, all terms are equal to 0, so it satisfies the PDE. Yes, there's a jump discontinuity, but this solution here has a discontinuity as well. And so the question is, why is this solution better than this solution? In other words, let me put this back to x. In other words, if the goal is to just find a function that satisfies this problem, and we're allowed to have that function be discontinuous, why not just use this function? And the reason is because we should never really disconnect the math from the physics or from the whatever, the real world, quote unquote, applications of the problem. Okay, this right here does not have conservation of wood chips. This does satisfy conservation of wood chips. And I invite you to pick a value of t and integrate from x equals that point to x equals that point, and show that it's always going to be equal to 1/2. And even better, you can kind of do this a little more generically if you write this as the t derivative of u plus the x derivative of v times u, and then think through it that way. Use some geometric properties of the curves, things like that, to show that we're always going to have conservation for this type of solution as well. And so this is the the primary reason that we pick this solution over something kind of silly like this. Mathematically, maybe if we just forget about where this comes from, both of these things could be called solutions to that problem, but this is the only one that is kind of consistent with the physics of this situation. Because remember, we derived this equation using a conservation law. The solution should satisfy the conservation law. Okay, but again, if we forget all of that and just have that differential equation, both of these solve the PDE, or solve this Cauchy problem that we have there. Okay, we are going to look at another example. It's going to be very similar to this one. And we're going to use the same method as well. We're going to use the fact that we can write the slope as 1 over that and kind of work through that a little bit. Just two different perspectives, or one perspective we saw last week, another perspective that we're seeing this week, as a way to solve these first order PDEs.